Currently, there are thousands of exoplanets that have been discovered, and they range in sizes, masses, their orbits. So some are close to their stars, some are a long way from their star, and these are planets that are orbiting stars other than our Sun, which is the exoplanet part. But is it possible for a planet to have an orbital period of less than 1 hour? Well, in this video, we're going to have a look to see if that's possible, and if it is possible, which planets are they? So first we're going to start with this object here. So this is a planet mass object and it is orbiting a pulsar. I'm not going to read the name out, but it's down at the bottom there. And this is the shortest orbital period of a planetary mass object found to date. So the pulsar is a very small, compact neutron star which is rotating quite fast and has these kind of beams coming out of its magnetic pole, which gives a pulse every time it rotates. And these are like stellar remnants from a fairly large star, so a star larger than our Sun. And then you have this planet mass object on the left, which is actually losing material to the pulsar. So the pulsar is pulling material off, and it's then essentially growing the size of the pulsar at the same time. So the actual system itself is around about the size of the Earth and Moon system. So the separation between the pulsar and this planet-sized mass is about the same. Now that gives it an orbital period of about 48 minutes. So that is less than 1 hour. So you've got this planet-sized object orbiting a dead star, essentially, this stellar remnant, in less than 1 hour. And just to give that context, that's the same distance that separates the Moon and the Earth, or thereabouts. However, it's a little bit smaller than Jupiter on the left, the actual planet itself, and its mass is quite high. So it's a lot denser than Jupiter. It has a mass about 8 times that of Jupiter compared to just under 1 times its radius. And then the pulsar, because it's a stellar remnant, it's a very dense, compact object. It's basically the central core that's left behind and it's collapsed and is being held up by neutron degeneracy pressure. And it's about the size of a city, actually. So radius is about 20 kilometers and it's just under 2 times the mass of the Sun. So it's a very massive object in the sense that it has a lot of mass. So it's almost twice that of the Sun, but it's a very small, compact object. So it's a very dense object. And actually, the small size of this object is quite important when we come to have a look at the actual orbital period and how close these objects are. So it orbits a pulsar, and if you're not familiar with what pulsars are, they're basically a very fast neutron star. Pulsars and neutron stars are probably about the same thing. But with a pulsar, they have these beams or these jets coming out from the magnetic pole, and the magnetic axis is offset from the rotation axis. So as it rotates, these beams kind of sweep out. We pick up one of those each rotation, and they do that very, very fast, actually. And this particular pulsar is rotating about 182 times a second. So it's an incredibly fast rotating object. But it's also worth thinking about, you've got these very powerful beams being swept out very, very fast, and you've got a planet-sized object very close as well. So if you did have a planet, we can be fairly confident that it's not going to be habitable in this system anyway. But this object is not actually a planet. It might be planetary size. I mean, it's quite a massive object. It's like nearly 8 times more massive than Jupiter, but size-wise in its radius, it's about the same as Jupiter. And it's actually the remains of a core of a star. So it's not a full star, it's what's left of the central part of a star. And we'll see why that is the case, because it's basically lost its outer layers. So the material that it's lost from its outer layers has basically been transferred to the pulsar. So the pulsar has pulled material off, the pulsar has essentially increased in mass, and its companion star would have lost mass, and it leaves behind this central core, which just so happens to be planetary size, planetary mass. Now what happens here is you'd have 2 stars. They're in a binary system. So quite a lot of stars are in binary systems. They orbit a common center of mass, and they're not going to be the same mass as each other. So one of them will be bigger than the other, and when they go through their normal evolutionary cycle, the more massive star will end or come to the end of its life sooner than the smaller star. It might sound bizarre in the sense that they should have more fuel available to them, but actually they become more efficient at using that fuel the bigger they are. So the bigger star actually ends its life sooner. So the star that is now the pulsar would have had a type 2 supernova, which then leaves behind the pulsar. That's obviously problematic for the companion star and any planets that may or may not be there. But then you have this other star, which is likely to be more the size of the sun. So a sun-like star is going to go into a red giant phase. It will swell up. So once it leaves the main sequence, it swells up in size. When it does that, material is closer to the pulsar, so it gets pulled off. It then creates this accretion disk around the pulsar and then falls onto the pulsar. But in doing so, in order to conserve your angular momentum, as that disk rotates around the pulsar, then falls onto the pulsar, it actually spins the pulsar up. So these systems here is one mechanism in which you can actually speed up the rotation rate of a pulsar. Normally, they slow down. So those beams that they create, those jets that sweep out, you get a magnetic braking from that, and over time they typically will slow down in rotation. But when you have a system like this, it will actually spin up the pulsar. So this is responsible for removing much of the outer layers of this companion star, which is then left behind that central core. Now, we're going to leave that system behind and forget about it really, because it's not really a planet. Yes, it has the shortest orbital period of a planet-sized object, but it's not an actual planet. The shortest orbital period of a true planet that we would typically think as a planet and not the remains of a star is actually considerably greater than the 1 hour. So it's about 4.25 hours it takes to go around its star. Not going to read out the name again, but it's up there at the top. It orbits a red dwarf star, which is again a very small star. This is a fraction the size of the sun. You'd typically be looking about 1/5 to 1/4 the radius of the sun, and then the same again for the mass. So they're quite a small star, which means it can be quite close again. So this is our shortest orbital period of a true planet. There are a few other planets that are kind of around about the same orbital period, but a few minutes longer. But this is the shortest one. Now, to put that in context of how close that planet needs to be to its star, if it was orbiting the sun, it would be skimming the surface just under 200,000 kilometers away from its surface. It would be incredibly close, only just away from its surface. I mean, 200,000 kilometers sounds like a lot, but in astronomical terms, that's actually really close. So it would be skimming the surface of the sun if it was orbiting the sun. Good thing is it's a red dwarf, which means it's actually much smaller. Now, to put that into context of the Earth, it's actually like a mini Earth. So it's a terrestrial planet. It's just over half the radius and it's just under half the mass. So it's kind of like a mini Earth or a typical terrestrial planet, we might think. And it's probably worth noting that due to its very, very close orbit and the distance between that and the star, it's unlikely to have a significant atmosphere associated with it. So it's likely just going to be rocky, really. It's not going to have a massive atmosphere, if anything, at all. But the more intriguing thing about this planet is because it's so close and such a short orbital period that it's going to be tidally distorted. So the tides, the gravitational force from that star is actually going to elongate it into more like a rugby ball shape or more elliptical shape, like you can see here. And that's because it's so close, and it's expected that it's going to be a significant deviation away from a spherical planet. That's purely due to that separation distance, really. Now, something worth noting as well, that the first system we had a look at, which was the planetary sized object orbiting the pulsar, is that separation there, which is about the Earth-Moon distance, is actually shorter, or the distance is smaller than the radius of most stars. So, for example, the Sun, it will be well inside the radius of the Sun. So that immediately gives you a problem, because if you can't have a 1 hour orbital period around a typical star, because the radius is going to be inside the radius, and you can't have an orbit inside the actual star itself. So what that basically means is if you want to have a orbital period of about 1 hour, then it's likely going to be a stellar remnant, which means that it's going to be something like a white dwarf star, a neutron star, pulsar, black hole, because then they are much, much smaller in radius. Their mass is obviously fairly high, but their radius is quite small, so it means you can get really close. Now that gives you some really big problems for the planet itself. Like, how did it get there in the first place? Because if you've got a stellar remnant, if it was a white dwarf, it would have had to have gone through a red giant phase, and a planet that close would have been basically swallowed up by the star at that point. If it was a neutron star, pulsar, black hole, they would have gone through a supernova explosion at the time of their death. That's going to destroy or cause some significant problems for a planet, and most likely destroy it anyway. So if you have got a planet that close, you need to start asking questions: where did it come from? So at the moment, the shortest orbital period is about 4 hours. Are we going to find any closer, or is that kind of the limit? Thank you for watching, and if you enjoy, then check out some of the other videos.